Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome. So, actually, a few months ago, I was talking with Asaf and Gian about a problem, delicate problem on branching processes, and we found some way to work around it. And then I was really delighted when Svante offered to talk on this very same issue. So, all right. So, very happy to have Svante Jansson from Uppsala telling us about conditioned Galton-Watson trees.
Okay. So, to begin with, even if many of you know it, let me say what a conditioned Galton-Watson tree is. So to begin with, we're a Galton-Watson tree. And see now, since this is a software company, I'll draw it in the computer science way, we're upside down. So we start with a root, and then we have first take an unconditioned Galton-Watson tree. Take a root. It has a random number of children, some number of offspring called some offspring distribution. Each of them have children according to the same distribution. And some of them don't get any children at all, like this. So each node has, say, IID children. And I use, if I need it, I don't know if I need it really today, offspring distribution, typically I denote by a Greek xi, or this is a random variable, a typical one of these. So this is the, say, standard type of discrete branching process, Galton-Watson process. And we think of this as a tree and are interested in properties like height and width of it. But, well, okay, so remember also the basic fact here that if the expectation of this offspring distribution is less than 1, then we call the tree subcritical, and then it dies out exponentially fast. So tree finite almost surely. If the expectation is 1, we call it critical. Well, there is one trivial exceptional case. If each individual has exactly 1 child, we'll of course get 1 infinite line. We forget that case or exclude it. Otherwise, it turns out that the tree is finite in this case too. It will almost surely die out, although the expected size is infinite. But expected, if t is the tree here, and this is the size of the tree, this is infinite. And this is something we will use later, so it's good to know directly that probability that the size of t is n will be roughly of n to minus 3 over 2. Whereas in this case, it will decrease exponentially. And I'm cheating a little. There may be some more or less trivial parity problems. For example, if you take a complete binary tree, the size is always odd, so you only consider odd n. But you're quite right. I need a second moment estimate for that. And that's why. So actually, I'm going to assume second moment estimate in what I say today. So this is true if we have second. Let's put it here. Today, we assume that the second moment is finite. And then we have the supercritical case when, well, of course, it still may die out, but we have a positive probability of having tree infinite.
Can you not use that height anymore? Today?
Well, no, I'm not going to use the supercritical case, so don't worry.
No,
about it?
Well, only bits in that horizontal position as well.
Well, let's see. I'll move over here. Hope better. Now, I'm going to talk, we said, about conditioned tree. It means we condition on the size. So, take. No. Take one. So let's say Tn is, this Galton-Watson tree, which we called T conditioned on the size being exactly n. So this is what we call a conditioned Galton-Watson tree. A little liberty in notation, since of course you can consider Galton-Watson trees conditioned in other ways too, but this is the what I'm going to talk about. And then it's one important basic fact here, that one can change the distribution of psi and still get the same condition tree. If we, so I can, well, let me write that too. If, say, probability of psi prime equal to k is some constant, normalizing constant times some other constant a to the k times probability xi equals k, then xi and xi prime yield the same conditioned tree, same Tn, I mean same distribution. A simple calculation, do that. And that means that you more or less can assume that we are in the critical case, which is nice and natural. I mean, they're both, there are certainly several advantages of being using the critical case. So we can now, using this, assume one, so it's critical. Well, almost. To be more precise, this is if we are in the supercritical case. Well, if we take a less than 1 and write normalized constant c, this is always a well-defined distribution, and the mean will be a continuous function of a and so on. So we can just choose to write a, so we get a critical 1. In the subcritical case, that is not always true, because then we need to take a greater than 1. And what one should do is to look at the probability generating function, and if that has infinite radius of convergence, or if it has finite radius of convergence and goes, for example, to infinity at the boundary zone, there is no problem. But there are cases, if you, for example, let these decay like the power of k, then you certainly cannot take any a greater than 1. So if you are in a subcritical case with some power law tails, then you can't make this shift to critical 1 version. And that's a case that I don't think anyone has really studied seriously. And one of my co-authors, what I'm going to talk about today, pointed this out when we met a few weeks ago, that that's a case that where one can wonder what happens. And it seems that I think we at least convinced ourselves that things are not so nice in that case. One cannot state so good general theorems. But I'm not going to worry about that today. So today I will assume that we have reduced to critical case, that we can do that, and that we have finite variance. And one reason that these trees are studied so much is that they contain, I mean, we choose different distributions xi, we got different distributions, different classes of random trees, and they include many of the standard random trees that appear in various applications. For example, if we take random uniformly labeled tree on n vertices. Or if we take a binary tree on n vertices, again uniform among all labeled binary trees, or several other standard versions. You can read about that in, for example, David Aldous' old paper on continuum random tree, where he studies such trees in a lot. And I'll come back a little bit later to those papers again. Now,
The question.
yes?
When the tree is cut size n and it's conditioned,
Yes.
does every leaf node try to have children with the same probability distribution independently or simultaneously, or it's like one by one?
Well, I don't think it matters if you do it simultaneously one by one. That doesn't matter. You can take them in any order, since they have the same distribution and they are independent of each other. Now, two things you can study. Of course, you can study several things, but the two things I will study are the, say, height of, let's call it h of Tn. So height is the maximum of, let's say now, d denotes the distance to the root, and v is the vertex. So here is vertex v, and this here is distance d of v. And well, for the width, let me denote width at a certain level. WL of Tn, that's the number of vertices v that have this distance or depth equal to L. So here is, for example, this must be depth 2. W2 in this case is equal to 3. And width of the tree is width is equal to, let me denote it by WT, and that's the maximum over else. And now one thing which is known, has been known for a long time, that these are both of the order of root n. So actually I want to be a bit more precise here and tell you a bit more about the background. So although that means I have to go back to what David Aldous did about 20 years ago. So it's a bit silly that I should tell him about it, but at least I can tell it to the others here. So one way to do this is to look at, one can code a tree using walks in at least two different ways. Interesting. We have, which also means computer science, if you want to go through all the vertices, there are at least two standard ways of doing it. You have the depth first search, or say depth first walk, which means we start at the root and then we find its children. Then we take them one by one, start here and take its children. So in that case we go here and down, and then we reach a leaf, we backtrack and we go through all vertices like this. So that's the depth first walk, we can call it. So if we do this in a computer, it means that we reach vertex we are looking at, we find all its children, and then we put them in a stack and process them one by one, and when we've done them we continue with we backtrack, go down in the stack. If we instead put them in the queue and take them in the order we have found them, it means that we start with a root, and then we first go through all its children, then we go through their children in order, so we take the grandchildren and so on. So that's the breadth first walk, say. or breadth first search, maybe it's better to say in this case. You can code both of these as a kind of random walks. Well, if we take the depth first walk, we will not get independent increments, but we can plot it like this. Depth first walk. We start at 0 and go actually to 2, and since we traverse each edge twice here, or maybe it's 2n minus 1. So we start, if we just plot a distance from the root, we'll get something. This will not be perhaps exactly the same tree as we had, but something like this. What David proved was that this depth first walk, if we scale this properly, it will converge to a Browning excursion. Excursion, let's call it E of t. If we look at the breadth first walk, well, if we count how many nodes we have in the queue each time, so how many vertices we have found but not yet processed, we will see that that is actually a simple random walk conditioned on return to 0 at the right place. So let's take the breadth first walk. So let's say q at time t is the number of vertices found and not processed at time t. And if we make a picture of that, it will look something similar. Well, it's a bit different. Here we have all increments of just plus minus 1. Here we can jump up by several vertices at the same time, but we always go down by only by 1. If you think of the way we do this, I mean, we find a bunch of children, but we always process one at a time, remove it from the queue. So this is actually can describe as a sequence sk, let's say sk tilde, from k equal to 0 to n, where sk tilde is sum I equal to 1 to k of psi I minus 1. And maybe we should start with 1, I think, where these are IID, the number of children of the different nodes. And so this is a random walk, but we have to condition on two things. First of all, this should end after n steps, so but not before. So sk tilde is strictly greater than 0 for all k, as I say, it's conditioned on. For k less than n and Sn tilde is equal to 0. So in other words, the first return to 0 should be exactly here. Well, actually it starts at 1, not 0. But we don't see that if n is large enough. And then this is a more standard thing in probability theory. Take a random walk and condition like this. And then it has been known since even longer back in time here that if we scale this, this also converts to a Browning excursion. So we get two Browning excursions for the same tree, but there are certainly different Browning excursions. Somehow one of them corresponds to the local time of the other in some sense. So let me say one thing. If we now want to find a height or width, we can read them off more or less, at least from both these. So the height, for example, is certainly the same as the maximum value of this depth first walk. Well, if we want to have the width there we have to look at the number of nodes at different heights. That's essentially the same as number of points different height here, which will converge to the local time of this Brownian excursion. And so let me continue for a while with colors. So depth first walk, that one. This leads to that if we take the height Tn and the width Tn joint distribution, and we scale, so we divide both by root n. I mean, I haven't written down the exact scaling, but I should say one important thing here. It's we always get the same limit here, but there's one parameter only. In the scaling comes in the variance of this psi, and it comes in different directions. So this height here will be proportional to 1 over the standard deviation, say sigma. The height here will be proportional to sigma instead. And here it's not surprising. I mean, if you have that the variance here obviously comes in, as the root of the variance comes in as a right normalizing factor for the height, that it goes in the opposite direction is not so surprising, because what I'm just going to say, that the maximum here will be the width, more or less. So if sigma, the standard deviation, is large, it means that the width is large. And if the width is large, you expect the height to be small, and conversely, since the total area is given to be n. So that's not surprising. But this will converge to, except that now I've forgotten the correct scale factors, but see now, maximum this Brownian excursion, and see now, I think it's I think it comes in the maximum of the local time here for it, and then with some constants, which I probably something like sigma there and maybe 2 over sigma here, but I may have constant wrong, and I just forgot in my office the paper where I have this written down. This also is some old results in any case. Constants you can check if you really need them. But for the breadth first walk, you get a similar thing. You can also read off both the height and the width. The width here is not exactly, but it's easy to see that it's roughly the maximum of this walk here. So it will convert to, in the scaling here, sigma times the maximum of Brownian excursion, and maybe again there's some constant 2.5, so that I've forgotten. And the height, well, then you have to, the height is really the number of generations we have if we do the breadth first walk. And since each generation, now this, the height here, which is in the limit corresponds to this Brownian excursion E of t, tells us how many nodes we have in each generation. So we get 1 over this E of t, tells us how fast we proceed, how many generations we move for each vertex. So we take total of that, we'll get the integral dt. And we get the 1 over sigma. So the interesting thing here, I found this a bit amusing, interesting at least, that is that we can obtain for the joint distribution of height and width, asymptotic distribution, we can express that in terms of Brownian excursion in 2 ways which look completely different. But of course we know that these 2 limits are the same. So that is some interesting identities for distribution for Brownian excursions, which I think were found before someone realized this, really. Well, this is a kind of background. Well, I should say also one thing more when I talk about this. So it means that these 2 things, note that the maximum appears in 2 different places here. So that means that if we do the right scaling, we have the same limit in distribution for the height as for the width. And that distribution is also known explicitly. One can write down nice generating functions and so on. But one thing, even if we scale things so that these things take the right sigma, these things will have the same marginal distributions. Therefore, I mean, marginal distributions are both this maximum bounding excursion. If you take sigma to be root 2, in case my constants happen to be right here. But I once proved that it is not symmetric. I mean, it's a two-dimensional distribution with the same marginals, but I was able to compute some moments here, at least numerically, and I showed that it is, if you look at the mixed third moments, they are not the same. So this is not symmetric. So there are some limits to symmetry involved here. But now I want to proceed to some more recent things. And that is, I'm interested not just in limiting distribution, but also want to have good bounds for moments and for tails of these. So say I particularly want to know probability that this is substantially larger than root 10. So this ratio is big, and find good estimates for that. And this is, I should say, joint work with Luc Devroye and Louigi Addario-Berry both in Montreal. And it is not yet completely written. It's not yet written up at all, and not yet completely proven. I'll come at the end to what is still open, which we hope we can prove. But I can at least begin with what is proven. See now. So let me continue yet another way. One thing which, well, this is again is not really new. This is certainly is quite old. Let me begin with looking at this width, WL or Tn. If we have fixed L, this is well known, easy to see that this converges to exactly 1 plus L times sigma squared as n tends to infinity. Now for fixed L, and sigma, so sigma square is the variance of xi. Should have said that earlier, or maybe I did. So at the beginning, these grow at linearly with L. Of course, that can't go on forever. Typically, we'll go on up to about root n, when the width will be root n. But then, it will die off again. And note here that if we take just the Galton-Watson tree without conditioning, we have, since it's critical, we have the expected number of children in each generation is exactly 1. So the conditioning changes this a lot. Now, I showed once in an earlier paper that we have actually uniform bound here. I mean, this was limit, but we also have a call it theorem. This is bounded by some constant c times L. Well, okay, if L is greater than 0. And this constant c, as all other constants I'll mention, they will depend on the distribution of xi, but not on my n or L or whatever else integers I'm talking about. Okay, so this is good for small fixed L. But now let's move on to a growing L, especially L in the range of n, of root n. So one theorem we can say here is that, well, let me write down several versions. Let's begin with the first thing. If we take not just WL, take the maximum of all of them. The width here really is of big O of root n. So this seems to be a quite fundamental result. We've looked here at the convergence distribution, and then it's of course very natural to assume that the mean here will converge to the mean here. And as far as I know, if you assume a bit more, at least if you assume exponential moments, which is what people typically do in case they are work with a generating function. I mean, as you know, one school of people doing probabilistic combinatorics does that by looking at the functional generating functions, and then it's very tempting and natural to assume that they are analytic also in a region outside the unit disk, which is equivalent to saying that we have some finite exponential moment. I'm not so sure yet about the history and literature, but I think that this has been proved in that case, but not in full generality. I don't know. Do you know anything more about that?
I think not in full generality.
Yeah.
That's probably the right answer.
But let me go on also and say that we also have better result. We can also take higher moments here. Let's take kth moment is exactly what you expect, big O of k over 2 for any fixed k greater than 1. And here's something which I find interesting. We can do the same thing here. Maybe I should have done that earlier, but as I said, this is work in progress. If we take a fixed L and take the kth moment, this is now of the order of L to the k, provided we have a kth plus first moment. And actually, in this case, I mean, the limit is some kth degree polynomial in L. But this assumption really is essential. This is an if and only if thing. I mean, this is quite easy to see, because here we only look at a finite level L, so we only look at finite part of the tree, and you can just as well look case when L is equal to 1. Just look at the number of children of the node, and it's not difficult to show this. And it's not so surprising, I think, that if you want to have some bound on the moments here, you want bound on the moments of the offspring, number of children of the root, say. What is interesting here is that you do not need any such assumption. And of course, one thing is that the scaling is different. Here I don't scale at all. I mean, here we say divide by root n, since we have the big of root n thing here. But even so, I find it a bit surprising, and can. At first, when I started working on getting these type of estimates, I was, well, first maybe looking at the height. I'll come to that later. But same problem for the height. And to begin with one thing, we have scaling here tells us that if sigma is large, so we have large variation on number of children, well, that will not really increase the height. That will keep the height down. Which is not surprising, because if you occasionally have very many children, well, it's not so surprising that that will tend to make the generation sizes wider on the average. So the width will be large, but that will just decrease the height. You run out of persons soon, so you have to stop. And for the same reason, I thought that, well, you don't need any higher moment conditions in order to get good estimates for the height. But I thought one would need that for the width. But that turns out to be wrong. When we have this, and let me put down even more corresponding exponential thing here. The probability that the width is, say, greater than or equal to k is bound by some constant e to minus a constant k squared over n. I said uniformly in k and n. This is now for all k and n.
This is just a consequence of the
No, but it's on the contrary. This is stronger. So this is a consequence of that. Because this says that if you take the width divided by square root of n, it has tails that go off exponentially fast. Well, actually like e to minus x squared.
It's a consequence of the moment bound if you can get the big O there uniform in K.
Yes. Okay, but
that's what it's
okay, but the big O here is should not be uniform in K. So maybe I was a bit sloppy, but I'll say this for each fixed K. But this is, as I said, uniform in all k and n. And the reason...
excuse me, and so sigma comes in the constant?
Sigma comes, yes, as I said, the constants depend on not just sigma, but they may depend on the distribution.
Is exponential bound? How does sigma come in the constant?
Well, I mean, I just claim that this is true for some constant depending on the distribution, and also sigma. I don't claim that this is uniform over all distributions of psi. Certainly sigma should enter here as a scaling factor, but maybe other features of the distribution too, like tails of psi or so will affect the constant here. I have not investigated that at all. And I don't think I intend to, but maybe someone else will.
I'm just curious.
Yes. But I mean, we know that the width it will be typical values of width will be, grow like sigma. You have a factor sigma here for the mean, for example. So that is what you would expect. At least for the first thing is that you have a constant divided by sigma squared here. But as I said, I don't think that even that is uniform. But I don't know, after having proven this thing, I realized that the reason is that we can get such bound without assuming any moment conditions and further moment conditions on the offspring distribution. Is that even if we say here at the first generation or second, we'll get an enormous number of children with a not too small probability, we still have to finish the tree so that the total size is n. And that means that if we have very many trees here, if we look at, for example, at the breadth first walk, it means that we reach some quite high level and have to descend to 0 in this predetermined time. So we have to get this remaining sum of independent random variables has to be now much smaller than its mean. And when we go, note that when we go down, we always go down by at most 1. So that means in that direction we are not helped by the fact that we may have large tails in distribution. So this is, one easily gets the same bounds there as if we had just sums of the bounded random variables. And it's easy to see that you get this Gaussian behavior, not just as a limit, but actually as a bound for finite n and k. And that translates into this result for the width. I don't want to go into detail, but I mean that's exactly how we prove this. So to be more precise, if k now is large here, to look at this probability, we look at the stopping time. The first time this random walk hits a height k, and then from that stopping time we know we have to descend to 0 since we have this conditioning, and it follows by straightforward estimates for sums of independent random variables. But I would not take the time to write down the details.
Do you also have the other tail?
For small k, I've not thought about that.
Small constant times square root of n.
Yes, I understand. Small constant. No, I have not. But that's an interesting thing too. I know that the limit here is such that these limit variables, they have all. Yes, I mean, it has them. I mean, all positive. All moments are finite, but also all negative moments. If you take 1 over this limit variable, it has all moments finite, which means that the probability of having very small value here is rather small. And but I don't know any. Should be fast. I mean, the probability of being less than x times root n. So in the limit, it will decrease faster than polynomial in x. It will decrease faster than polynomial in x as x goes to 0. Yes.
In the limit.
Yes, in the limit. But I don't know. I've not thought about that here. So that's a good open problem.
But if you get a bound about the length, wouldn't that imply? If you get a similar bound about the length.
Yes, that's right. That is, I think, yes, you're right. If we take the width here globally at maximum, you're quite right. Because if this is less than, say, epsilon root n, the height has to be at least 1 over epsilon root n, which will give strong bound, as I will show you soon. But one can ask the same thing for a fixed L. Say L is another constant times root n, and you look there whether we would expect again some very small probability of it being less than a small constant times root n, but I don't know. But instead, let me proceed and say that one thing, one can combine these things and also show things like this follows easily by just combining results above, but it looks nice, I think. If we take the width at height L, it is, I had the L here, and I had the exponential decay here. One can, I think one can get this. Well, okay, well, I have to combine some more results for height, but this at least is what we will what we can get. And now, said for the height, let me go on. That is where I. So for the.
In your abstract, you wrote that you managed to use some version of the size-biased.
Exactly. I want to say that. I know I have only a few minutes left, but the main another main tool here is that we use the size-biased Galton-Watson tree, and that's a paper by Peres, Robin Pemantle, and Lyons, I think. And the idea there, what they did was they looked at an infinite version of the tree, and one way to express this, say that we start with an infinite spine like this, and then we go on and attach. So the way I think of it is we have a line of more immortal people. Each immortal individual has exactly one immortal child. And the total number of children is not given by the same distribution here, but by the size-biased distribution. But then all other children are mortal, and they have children in the same way. So we take the spine and attach independent Galton-Watson trees all the way down. And it turns out that if one looks at that tree restricted to some height here, what we get is, we just look at this portion here, the same as taking the Galton-Watson tree, but size-biasing it, meaning that we size-biasing by number of individuals in this generation here. And so that is what we do to look at the distribution of the number of individuals at a given generation, we look at this generation L is better, not N. We do the size biasing up to generation L, but after that, all individuals are mortal. So we will not have this infinite spine. We only have a spine of length L, and then here we'll also attach normal Galton-Watson trees. That means that if we, for example, want to have the width at this level, expected value of the width at this level, thing I wrote at the bottom of Blackboard, one looks at this tree here, and what comes out? I mean, we have condition on size being n, so what is essentially in computation's calculation is the probability that this size-biased, finite version of this size-biased Galton-Watson tree has size exactly n, and compare that to the probability that the unconditioned tree here is size n, which is, I said, n to minus 3 over 2. I'll skip the details calculation, but let me just say that doing that calculation, using this tree here, we get this result for the width. And if we now want to go to the height, we use this result, as I just said, we say that probability of the height being greater than k. This is same as probability that the width at k is at least 1. So by Markov's inequality, this is at most, I should have some constant there. Constant times k e to minus k squared over n. Well, if k is like root n, this is not good because it gives you root n. If k is a little bit more, say at least root n log n or so, and then we can kill this off by changing constant here. So we think, well, let's call it conjecture, since we've tried to prove it, but there's still a gap in the proof. So e to minus constant k squared over n. So this is proved for k greater than, say, log n over log n times root n. Well, I mean it's immediate consequence of what I've written here. I think that I now run out of time, so I end with this thing. So I said we are. I just say that the idea here, both intuitive and the way you want to prove it, is say that, well, if there is one element large, height larger than k, then probably there are lots of them. Let's say at least root of them, or some called constant times root of them, if not at that level, so at least of a level which is, say, level k over 2. And then one should be able to, and then one can use this bound. And we have good reasons to believe that, but so far it hasn't, looking at the conditioning where the other virtues can sit, they ought to be rather uniform distributed, but we haven't been able to get the conditioning correct yet. So, as I said here, this uses basic ideas from at least 2 persons in the audience here, but I haven't been able to go into details in exactly what they have done or what we have done, but I hope I've been able to convey some of the main ideas here. So if you want to know further details of the proof, we can discuss that later. Okay.
Any more questions or comments?
I guess I think of the Brownian exertion results as being sort of somewhat robust to the model, sort of any, not any, but lots of sort of reasonable models of uniform distribution on some class of size n trees. This works for. I mean, people actually, I think recently have done stuff with the sort of unlabeled trees, which of course are technically much harder to work with. I mean, this is looking at, tied very closely to the Galton-Watson model. I mean, do you think there's any chance of doing this sort of thing for a little more robustly?
I'm not sure. Of course, it seems natural to ask the question, and presumably things are true in greater generality, but then comes the question how to do it. So I don't know how to do it. I mean, Galton-Watson trees are easy to handle technically. That's another advantage with them. Again, so one thing I said we've been doing here is to do this under minimal moment conditions. I mean, for example, the result for the height here, I should say, that was proved by, I think, Flacheolet and Odlyzko a long time ago, assuming exponential moments, even if they didn't state it in that way.
Which
this thing here, yes. If I remember correctly, that is some bound of that type is in one of their papers. But they used the analytic method and assumed higher exponential moments. But what you say about going to other trees, I said I really don't know. So I think I better leave that as an open problem.
So there you have a k squared over n.
Yes.
Right? And you said you can use it for log n if k is bigger than log n over root n.
Yes, it's because when this exponent is bigger than log n, so you can just, if I move this, you can kill this k here. It doesn't matter. So then this is the same as that, really.
I would think that root log n would be enough. Why?
Yes, okay. I was just making simple, but you're quite right. If we have large constants on root log n, that's fine, good enough.
I can breathe again.
Yes.
Right.
Right. So if any one of you has a good idea to prove this, I'm here for another week.
But if not, you're not.
We go somewhere else.
Okay, let's thank Santa again.